Hello everyone, welcome to video lecture of ME312 Metrology and Instrumentation. I am Manu Joseph, Assistant Professor, Department of Mechanical Engineering, Rajagiri School of Engineering and Technology. Module number 6, lecture number 1. In this lecture, we will be discussing about strain and stress measurement, electrical resistance strain gauge, its principle and operation. Strain and stress measurement. As we know, the strain is change in dimension by original dimension when a body is acted upon by a force. And also we have a relationship between strain and stress and Young's modulus. So Young's modulus is equal to stress by strain. So by knowing the strain, we can calculate the stress. So here in this lecture, we give importance to strain measurement, and as we know, once we could measure strain, it can be used for measurement of stress. So when a force or load is applied to a body, it undergoes some deformation. This deformation per unit length is known as a unit strain or simply strain. It is denoted by epsilon and given by the following equation: epsilon is equal to delta L by L. Epsilon is equal to delta L by L, where delta L is the changing length of the body and L is the original length of the body. The strain gauges are essentially employed for two different purposes: to determine the state of strain existing at a point on a loaded member for carrying out strain analysis, to act as a strain sensitive transducer element in the measurement of quantities such as force, pressure, displacement and acceleration. So it has two functions. One is to measure strain, other is to measure force, pressure, displacement and acceleration by measuring strain. The strain measurement are made over shortest gauge length, because the change in length measured over a finite length does not give value of strain at fixed point, but rather give average strain over an entire length. Therefore we generally carry out strain measurement over a short gauge length. A magnification system is essential since the change in length is over a small gauge length. There are two types of strain gauges. One is mechanical strain gauge and other one is electrical strain gauge. First one is mechanical strain gauge. A Berry strain gauge extensometer is used in civil engineering for structural application. That is the mechanical strain gauge. This was designed by a professor, Herman C. Berry, in 1910. It is employed for measuring small deformation under a linear strain condition over a gauge length up to 200 millimeters. Here, the strain obtained is magnified by employing mechanical means, as it is a mechanical strain gauge. For that, a lever system is employed for this amplification or magnification. So
mechanical strain gauge comprises two gauge points. One is a fixed point, other is connected to a magnifying lever. Both points are placed on the specimen. Main advantages of mechanical strain gauge is that it contains a self-contained magnification system. There is no need to use auxiliary equipment in mechanical strain gauge. So it's best suited for conducting static tests. So the main point we have discussed here is Berry strain gauge. It's a mechanical one. It consists of a lever mechanism to amplify or magnify the displacement. Here, one of the advantages is self-contained magnification system, because it doesn't require any additional equipment or auxiliary equipment for amplification or magnification of the displacement. And it is suitable for conducting static test. So some disadvantages of the mechanical strain gauge is response is slow as it is a mechanical system. It possesses inertia and friction. Automatic recording of reading is not possible for the system. Another disadvantage. It cannot be used for dynamic strain measurement and varying strain. So it's used for only static strain measurement. Dynamic, when the strain varying with the time, it cannot, for that this cannot be used. Next is electrical strain gauges. Electrical strain gauge. Previous lectures we have discussed about electrical transducer, where the physical quantity to be measured is converted to electrical form. Here in electrical strain gauges, change in strain produces a change in some of the electrical characteristics such as capacitance, inductance or resistance. The magnification of these strain can be attained by employing an auxiliary equipment. Compared to mechanical strain gauges, this required a auxiliary amplification system. Main advantage of measuring strain using electrical methods are their high sensitivity. They are highly sensitive. Ability to respond to dynamic strain. These are some of the advantages of electrical strain gauges. They are simple in construction, sensitive, linear measurement is accomplished. Strain gauges are inexpensive and reliable. There are two types of electrical resistance strain gauges, unbounded and bounded strain gauges. Unbounded strain gauge and bounded strain gauge. First is unbounded strain gauge. In the case of unbounded resistance strain gauges, the electrical resistance element or grid is not supported. A fine wire is stretched out between 2 or 3 points, which may become the part of the rigid base that itself is strained. So here we can see a rigid base. Rigid base is there. Then we can see 3 wires or grids stretched between 3 points or 2 points, 2 points or 3 points on the part or a rigid base, and the force is acting on this rigid base. When the force is acting on the rigid base, that when the rigid base gets strained, this wire also gets strained. As a result, there is a change in the length and dimension or diameter of the wire, and as a result, the resistance of the wire changes. So unbounded resistance wires are connected. 4 resistance wires are connected in such a manner that they act as full bridge. So these 1, 2, 3, 4 resistance are connected to a Wheatstone bridge. They form a full bridge. Full bridge means these resistance act as the resistance of 4 arms of the Wheatstone bridge. So that's called as a full bridge. So unbounded strain gauge are used more often as element of force pressure transducer and also in accelerometer. So unbounded strain gauge are used as an element of force pressure transducer and also in accelerometers. They are seldom used for strain measurement. So that's about unbounded resistance strain gauges. So in unbounded resistance strain gauges, the strain grids or wire is not bonded. They are stretched between 2 points on a rigid base. When the rigid base is strained, this wire grid also gets strained and its resistance changes. And this 4 resistance is connected to a Wheatstone bridge. It acts as a resistance of the arms of the Wheatstone bridge. Okay. So by varying the voltage or by getting the change by measuring the voltage on the Wheatstone bridge, you can measure the change in resistance and thereby strain. Another type of resistance strain gauge is bonded resistance strain gauge. Bonded resistance strain gauge. From the name itself, it's clear that it's bonded type. In a strain gauge, which is an appropriately shaped piece of resistant material, is bonded to the surface of material to be tested, is known as bonded strain gauge. That is, the strain gauge material is bonded to the surface of the material to be tested. Here, a thin wire in the form of grid pattern is cemented between thin sheet of insulating material. We can see thin sheet of insulating material and thin wire in the form of grid is cemented between these two sheets of insulating material, such as paper or plastic. The strain gauge may also be thin metal foil. The gauges are bonded to the surface of understudy. The gauges are bonded to the surface understudy using thin layer of adhesive and waterproofing, and is also provided by applying layer of wax or lacquer on the gauge. Here we can see the gauge material is bonded between two insulating material, and the entire arrangement is the strain gauge, and it is bonded to the material which is acted upon by a force. The gauges are bonded to the surface understudy using a thin layer of adhesive. So this is bonded using a thin layer of adhesive. And waterproofing is provided by applying layer of wax or lacquer on the gauge. The strain experienced by the grid and the surface understudy to which the grid is bonded will be same. So by making proper bonding, the strain experienced by the strain gauge and the surface on which it is mounted will be the same. So gauge is highly sensitive in axial direction, and in the transverse direction strain occur due to Poisson ratio effect. As we know, the Poisson ratio is equal to lateral strain by longitudinal strain. So gauge is highly sensitive in axial direction, and in the transverse direction strain occur due to the Poisson ratio effect. A cluster of 3 or more strain gauges, known as Rosette gauges, can be employed if the direction of principal strain is unknown. So in certain cases, when the direction of principal stresses, the principal strain or principal stress is unknown, we use a set of strain gauges arranged in a particular fashion at a particular angle. So that's called Rosette gauges. So the Rosette gauges are normally used in the measurement of strain in complex part. These gauges comprise 3 or 4 separate grid having different orientation and can be cemented to the surface of the part. So the resultant strain can then be gathered and recorded. So that's about Rosette gauges. In this image we can see Rosette gauges, and each gauges are separated by an angle 45 degrees. The bonded gauge exists in the following forms: wire type strain gauge, foil type strain gauge, and semiconductor or piezo-resistive strain gauges. So wire type, we can see the grid element is thin wire of diameter 0.025 mm. The grid is cemented in between two pieces of thin paper with a ceramic or plastic backing. This will facilitate easy handling of strain gauges. So here thin wire having a diameter 0.025 mm wound into a grid. Another one is foil type resistant strain gauges. In foil type strain gauge has a thickness of about 0.005 mm. It comprises a metal foil grid element on epoxy support. So we can see a metal foil. This is not a thin wire, it's a foil. It have a thickness 0.005 mm. They offer advantages such as improved hysteresis, better fatigue life, lateral strain sensitivity. They can be fixed on fillets and sharply curved surfaces because they are thin and have high flexibility. So this foil type resistant strain gauge, they are highly flexible. They can be placed on fillets. They can be placed on the fillets because they are highly flexible. Semiconductor or piezo-resistive strain gauge, they are certain strain gauges which consist of silicon or germanium and contain the impurities boron, precise amount of impurities like boron, which impart certain desirable characteristics. That is semiconductor or piezo-resistive strain gauge. So we have seen three type of resistance strain gauges. One is wire type, second is foil type, third one is semiconductor or piezo-resistive strain gauges. Then strain gauge material, normally we have constantine, nichrome, platinum, etc. as strain gauge materials. The grid material should have all or many of the following characteristics. We have 11 characteristics, 1 to 11. So the grid material should have all or many of the following: high gauge factor, high resistivity, high yield point, high endurance limit, low hysteresis, good corrosion resistance, etc. These are the different characteristics that a grid material should have. Backing or carrier material. Backing material provide support, dimensional stability, and some of the mechanical protection for fragile and delicate strain sensitive element. So this backing or carrier material provide support, proper support and dimensional stability to the strain sensing element. And we also use adhesives. Adhesive or bonding material are most commonly employed agent to bond the strain gauge to the specimen or test area in order to transmit strain to the gauge carrier and later on the strain sensing element with true fidelity. Fidelity we have seen as a dynamic characteristics of an instrument that explain the how reliable our instrument is towards a given input. So adhesives, as we know, the strain gauge has the ability to sense the strain only when the strain is properly transferred from the body on which the force is acting to the strain gauge. For that, a proper bonding should happen between the strain gauge and the body. So that is possible only by having a proper adhesive. A protective coating. In order to prevent the damage, they may be caused to relatively delicate gauge installation. It is essential to use protective coating. There are chances of mechanical damage, chemical damage, or damage by other environmental conditions. To avoid that, we have a protective coating for the strain gauges. So method of strain measurement. An electrical resistant type strain gauge employs highly sensitive resistance bridge arrangement, that is Wheatstone bridge arrangement for strain measurement. Here we can see a Wheatstone bridge. In the image we can see four resistance R1, R2, R3 and Rg. Rg is the strain gauge resistance. So this form a Wheatstone bridge. And Wheatstone bridge have two more part: an input voltage, then to measure the output, we can see here the output measurement. For that we have a galvanometer or voltmeter. Here in this Wheatstone bridge, for measuring strain gauge, one of the resistance is replaced by a strain gauge, and the strain gauge is bonded to the material whose strain is to be measured. So it can be assumed that in order to balance the bridge, balancing the bridge means this voltage across the voltmeter is 0. That is all the resistance are having equal value. Okay, to attain this, it is necessary that is B means is equal to 0 for balancing the bridge. Here the voltmeter having 0 reading. To attain this, it is necessary that ratio of resistance of any of the two adjacent arm and the ratio of resistance of remaining arm taken in the same sense are equal. That is, the ratio of resistance of any two adjacent arm, R1 and R3 ratio, that will be equal to the ratio of resistance of other two arms, R2 by Rg. So if this ratios are same, then V at the voltmeter is equal to 0. Then the bridge is said to be in balanced condition. In case any one of the resistance in case any one of the resistance change, the voltmeter will indicate a change in voltage which unbalances the bridge. So any of the resistance change, the voltmeter will indicate a change in voltage which unbalances the bridge. The change in voltmeter reading can be made use of complete change in the is used to compute the change in resistance. Since the change in resistance is indicated by a deflection of the meter, this method is known as deflection method. So in deflection method, the reading of the change in strain can be noted down continuously without any rebalancing. Here rebalancing is not required. And this method is not accurate because the tendency of the bridge output to become non-linear with change in strain. So there is a tendency that bridge output to become non-linear with the change in the strain. So here we can see a strain gauge which act as one of the resistance of a Wheatstone bridge. As I said, this strain gauge is mounted to the body whose strain is to be measured. At initial condition, R1 by R3 is equal to R2 by Rg. Then the voltmeter gives 0 reading. When the material is strained, that strain gauge which is bonded to the material will also get strained. As a result, a change in the length or diameter take place to the grid element of the strain gauge. As a result, its resistance changes. That means one of the arm of the Wheatstone bridge having a different resistance. Therefore, R1 by R3 not equal to R2 by Rg because the Rg value changes. So R1 by R3 not equal to R2 by Rg. Then V mean not equal to 0. This V means not equal to 0. So we can measure this V mean to find out the change in resistance, then to find out the strain. So here this is called deflection method because the voltage is measuring here by the deflection of the needle of the voltmeter. So deflection method. We are not balancing the strain gauge again. Once the initially is balanced condition, after the change in resistance of the strain gauge, it become unbalanced. But we are not rebalancing it here, directly reading the voltage. This is called deflection method, and it is not accurate because tendency of the bridge output to become non-linear with the change in the strain. So another type is null method. After each successive change in resistance, the bridge balances so that the meter is brought back to zero, thus nullifying the effect of change in resistance that is used for measurement of the strain. So here in null type, with change in the resistance of the strain gauge with the change with the strain, the Wheatstone bridge become unbalanced. There is a voltage variation, and what we do is we rebalance the system. We rebalance the system and do the measurement. So that is why it is called null method. In null method is superior to deflection method because strain indicator calibrated under null balance condition exhibit linearity and high accuracy. They have high accuracy and linearity. Here in this image we can see two strain gauges mounted on the two sides of a cantilever. So when this cantilever is strained, a load is acting on it. So this is bending, this is bending, this is bending. One of the strain gauge is under compression, tension, and one is under compression. Here we have compression and here we have tension. Okay. In a situation like this, what we do is we connect this strain gauge to one of the resistance of the Wheatstone bridge and this strain gauge to other resistance of the Wheatstone bridge, and then we could measure the strain experienced by this test specimen. Then one of the important term for strain gauge is gauge factor. The gauge factor is the most important parameter of a strain gauge. It is a measure of amount of resistance change for a given strain, therefore serve as index of strain sensitivity of the gauge. Is index of the strain sensitivity of the gauge. Mechanically it is expressed as follows: gauge factor GF is equal to delta R by R, that is change in resistance due to strain, divided by R divided by delta L by L. For a meter, delta L by L is equal to strain, lateral linear longitudinal strain, delta L by L. Therefore delta R by strain is equal to gauge factor. Delta R by R by strain is equal to gauge factor. Also delta R, that is change of resistance with due to strain in the body, delta R is equal to R into the original resistance, gauge factor R into gauge factor into strain. Okay, so in this we could find out the strain. A higher gauge factor make the gauge more sensitive, and the electrical output obtained by indication and recording purpose will be greater. So that is the importance of higher gauge factor. Higher the gauge factor, gauge become more sensitive. Gauge factor is normally supplied by the manufacturer and varies from 1.7 to 4 depending upon the length of the gauge. So it's a index of strain sensitivity of the gauge. Next is regarding the theory of strain gauges. The change in resistance value obtained by straining the gauge is attributed to electric behavior of the material. If an elastic behavior of the material. If an elastic material is strained by applying tensile load in the axial direction, its longitudinal dimension increases. So if an elastic material applied by a tensile load, its longitudinal dimension increases, so length increases, and lateral dimension reduces. There is a reduction in the lateral dimension, diameter reduces as a function of Poisson ratio. This lateral reduction in the lateral dimension is a function of Poisson ratio. The resistance of the elastic material given by the following equation. For a material, this is the equation for resistance. R is equal to rho L by A, where R is the resistance, rho is the resistivity, L is the length of the wire, A is the area of cross section. So here rho is the resistivity. So that is the relation between rho, L and A. After differentiation, when we differentiate, after differentiation and substitution, the gauge factor for the strain gauge is so we take the gauge factor, this is GF, gain factor is equal to dr by r by dl by L. Once we differentiate this, so this is equal to dr by r and epsilon A, and once we differentiate it and apply the differentiate and apply the gauge factor, will give 1 by nu plus d rho by dl by L. So after differentiation and substitution, gauge factor for the strain gauge is, this is the final strain gauge after differentiation and certain substitution, 1 plus 2 nu plus d rho by rho divided by dl by L, where nu is the Poisson's ratio. So electrical circuit of the Wheatstone bridge. The electrical circuit containing the strain gauge is as important as the gauge itself. So the electrical circuit is very important part of a strain gauge. Is the electrical circuit which relay the change in gauge resistance to a measurable change in the voltage. When Wheatstone bridge circuit containing the strain gauge as one of the resistance is popular choice for accomplishing this. So a Wheatstone bridge circuit with a strain gauge as one of the resistance of the circuit is the best choice for the strain measurement. It comprises 4 resistance arm. For a Wheatstone bridge comprises 4 resistance arm, an energy source and a detector. For resistance, 1 energy source and detector and a voltmeter. And for unbalanced condition, as we explained, V across the these 2 points will be equal to 0. So V mean equal to 0. So V mean is equal to V in. So here the voltage is equal to voltage at this point minus voltage at this point. So V in voltage at this point is equal to V in into Rg divided by R2 plus Rg. R2 plus Rg total resistance, R2 plus Rg the total resistance. V in divided by R2 plus Rg give the current across the circuit, current across here is equal to V in divided by R2 plus Rg, and so the voltage here is equal to V in divided by R2 by Rg into Rg. Similarly, voltage here is equal to V in into R3 divided by R1 plus R3. So that difference is equal to the voltage here, the final voltage here. So choosing a resistors such that R1, R2, R3 all are equal to Rg0. Rg0 means resistance of the strain gauge when the strain is equal to 0. So R1, R2, R3 all are equal to Rg0. The strain gauge resistance at 0 strain, Rg0. So then V mean is equal to 0 because R2 by Rg is equal to R1 by R3. So V mean is equal to 0. That is the balance condition. That means all the 4 resistance are equal. The bridge is said to be balanced. And we know that resistance of the strain gauge at a particular strain is equal to resistance when strain equal to 0 plus change in resistance due to the strain Rg0. The substituting in the previous equation, V mean can be written like this. When all the 4 resistance are equal, that is R1 equal to R2 is equal to Rg0 equal to R3, we'll get the equation like this. Then taking the LCM, we'll get the equation like this. And delta R is a tiny fraction of Rg0. As delta R is a tiny fraction of Rg0, the delta R term can therefore be dropped from the denominator. This can be dropped from the denominator because this is very small compared to Rg0. So the equation becomes like this. The substituting delta Rg, the change in resistance due to the straining, due to strain, by gauge factor, we'll get delta Rg is equal to Rg0 into gauge factor into strain. So substitute that, we will get the equation like this. Therefore strain is equal to 4 divided by gauge factor into V mean by V in. Only the gauge factor, the strain gauge factor GF, and the circuit excitation voltage V in are needed to convert measured voltage V mean to strain. So once we measure the voltage in the galvanometer or voltmeter when the material gets strained, by knowing the gauge factor and excitation or input voltage, we can measure the strain using this equation. So that is the basic principle of a strain gauge. So strain gauge always used in connection with a Wheatstone bridge. One of the method, the Wheatstone bridge, one of the arm of the Wheatstone bridge, its resistance will be a strain gauge, and this strain gauge is bonded to the material whose strain is to be measured. Initially the Wheatstone bridge is in balanced condition because all the resistance R1, R2, R3 and Rg0, they all are same. There is a balanced condition and voltmeter gauge 0 reading. When body gets strained, the strain gauge which is bonded to the body also gets strained. As a result, its resistance changes, and that result in a net voltage in the voltmeter which is connected to the Wheatstone bridge, because the Wheatstone bridge become unbalanced. So by knowing the relation between strain gauge factor of the strain gauge, V mean, that is the voltage measured at the voltmeter, and V in input voltage, we could find out the strain. That is the principle. Resistance change in temperature. So temperature has some effect in the strain gauge resistance. So we are going to study how to tackle that. So unfortunate characteristic of a strain gauge is that resistance change with the change in temperature. That is a unfortunate character of a strain gauge. So we can transcend this problem by using a strain gauge in the place of R2. The previous case we have seen, the strain gauge is connected only to one of the resistance of the Wheatstone bridge. Here the R2 is also replaced by a strain gauge. So this type of arrangement is a half bridge. So half bridge, Wheatstone bridge, half bridge. Other one is quarter bridge, okay. So both the element of Wheatstone bridge arm will change resistance in same proportion when temperature changes. So when temperature changes, both the arms resistance will be changing equally, thus cancelling the effect of temperature change. So both the gauges are bonded to the same test specimen. This is R2, which is also a strain gauge. This Rg, the strain gauge, other strain gauge. Both these strain gauges are connected to the test specimen, but only one is placed in the position and orientation so as to be exposed to physical strain. Only this one will experience a strain. The strain will be experienced by only this strain gauge. Other one will act as a dummy, and that is coupled to the or bonded to the material whose strain is to be measured, but it will not experience any strain. So other gauge is isolated from all mechanical stress and act merely as a temperature compensation device, because when there is an environmentally temperature of the environment changes, temperature of the body changes, along with the change in the resistance of the strain gauge which is coupled to the body Rg, this R2 resistance of the R2 also changes with that temperature. So R2 by Rg will be a constant, therefore R2 by Rg with change in temperature will be constant. Okay, so this method is used to tackle or compensate change in resistance of the strain gauge with the change in temperature. Here we can see the arrangement. Here this is the body which is active on axial load, this specimen. Here we have a strain gauge which acts as one of the arm of a Wheatstone bridge, another strain gauge which is connected to a body which is same body, a body of same material, but it is not getting strained. So when temperature changes, resistance of the both strain gauge also resistance of the both the strain gauge changes. Okay, so we can compensate the temperature effect of strain gauge resistance. Okay, so and this is a full bridge circuit. This image represents a full bridge circuit. We have seen quarter bridge, half bridge. This represents a full bridge. All the arms or all the resistance of the Wheatstone bridge is replaced by strain gauge. In application where such complementary pairs of strain gauge can be bonded to the test specimen, it may be advantageous to make all the four elements of the bridge active for even greater sensitivity. This is called full bridge. In certain application, for complete strain measurement, we need to couple 4 strain gauge. In those cases, all the arms of the Wheatstone bridge will be replaced by strain gauge. So that is full bridge arrangement. This is called full bridge arrangement. So in this lecture, we have discussed about the strain measurement. We found that there are 2 types of strain gauge. One is mechanical strain gauge and other one is electrical strain gauge. The advantage of mechanical strain gauge is amplification or magnification is mechanically, but it can only be used for static strain measurement. But in electrical strain gauge, we can measure the dynamic strain. Here the strain is converted to some electrical characteristics such as capacitance, resistance, inductance, etc. Then we discussed about resistance strain gauge. We have seen 2 types of resistance strain gauge. One is bonded type and unbonded type. Then bonded type, we have seen 2 types. One is wire type and other one is foil type. So we found what is the Wheatstone bridge is always coupled with the strain gauge for strain measurement, and the working principle of a strain gauge connected with a Wheatstone bridge. Here one of the resistance of the Wheatstone bridge will act as a strain gauge, will be replaced by a strain gauge, and the strain gauge is mounted to the body whose strain is to be measured. So when initially the bridge is balanced condition, so that all the 4 resistance will be same value, or the ratio will be same. But when the body gets strained, the strain gauge, the resistance of the grid element of the strain gauge changes. As a result, the Wheatstone bridge becomes unbalanced. This change in this voltage is measured, and by knowing the gauge factor and input voltage, we can measure the strain. So that is about strain gauges and strain measurement. Once we could measure strain, by knowing the Young's modulus, we can measure the stress. Hope you have understand the lecture. Thank you.